What if I told you that one of the harshest deserts in the world was split in half, not by nature, but by human engineering? In the heart of the Mongolian Desert, where endless dunes stretch beyond the horizon and violent sandstorms can swallow entire roads in minutes, China built one of the most ambitious infrastructure projects of the 21st century, a massive 2,700-kilometer elevated railway cutting straight through the desert. The Mongolian Desert, part of the Greater Gobi region, is not just dry, it's extreme. Temperatures can swing from -40 degrees Celsius in winter to over 45 degrees in summer. The ground constantly shifts, sand dunes move like waves, and strong winds can bury structures overnight. For decades, this vast region remained one of the most difficult terrains for large-scale construction. Traditional railways built at ground level often suffered from sand accumulation, track deformation, and constant maintenance challenges. But instead of avoiding the desert, engineers decided to rise above it. The idea was bold: construct a fully elevated railway stretching 2,700 kilometers across the desert landscape, effectively splitting it with a continuous line of concrete pillars and steel tracks. By lifting the railway above the shifting sands, engineers could prevent sand burial, reduce erosion damage, and maintain long-term stability. It was not just a railway, it was a strategic economic corridor designed to connect remote regions, boost trade routes, and support China's growing logistics network under major development initiatives. Planning began years before construction. Engineers studied wind patterns, sand movement cycles, soil stability, and seismic risks. Unlike traditional foundations built on solid ground, desert foundations require deep anchoring systems. Each pillar had to be drilled far below the surface to reach stable soil layers. In some sections, foundations extended more than 20 meters deep to resist shifting sands and strong desert winds. The scale of the project was enormous. Over 2,700 kilometers of elevated track meant tens of thousands of reinforced concrete pillars. Each segment had to be precisely aligned to maintain high-speed rail standards. Unlike older freight railways, this system was designed to support modern electric trains capable of transporting both cargo and passengers efficiently across vast distances. One of the biggest challenges was sandstorms. In the Mongolian Desert, sandstorms can reach wind speeds of over 100 kilometers per hour. These storms not only reduce visibility to near zero but also sandblast surfaces with fine particles traveling at high velocity. To combat this, engineers developed aerodynamic bridge designs that allow wind to pass through with minimal resistance. The elevated structure reduces sand buildup, while specially designed barriers in key areas deflect sand away from the tracks. Temperature fluctuation posed another major obstacle. Steel expands in heat and contracts in cold. In a desert climate with extreme temperature differences, rail expansion could lead to track misalignment or structural stress. Engineers used flexible expansion joints and high-grade steel alloys capable of withstanding wide temperature variations. Advanced monitoring sensors were installed along the railway to detect stress changes in real time, allowing maintenance teams to respond before small issues become major problems. Water scarcity was another unexpected difficulty. Large-scale construction requires massive amounts of water for concrete mixing and dust control. But in the desert, water sources are limited. To solve this, temporary water pipelines were built from distant reservoirs, and recycling systems were implemented to reuse construction water. Some sections even relied on transported water delivered by specialized trains during peak construction periods. Building such a railway in a remote desert also required the creation of temporary worker cities. Thousands of engineers, laborers, and technicians lived in mobile housing units equipped with solar panels and self-contained energy systems. These camps had to be designed to withstand sandstorms and extreme weather. At the height of construction, entire logistical supply chains operated solely to keep the project running in isolation. Environmental concerns were carefully considered. The desert ecosystem, though harsh, is home to unique wildlife and fragile vegetation. Elevated construction minimized direct contact with the ground, allowing animal migration routes to remain largely undisturbed. Special wildlife corridors were integrated into certain sections, ensuring that the railway did not become a permanent barrier to local species. From a technological standpoint, the railway represents a fusion of civil engineering and digital innovation. Drones were used to survey vast desert stretches quickly and safely. Satellite positioning systems ensured millimeter-level alignment accuracy over thousands of kilometers. Artificial intelligence analyzed wind data and predicted sand movement patterns, helping engineers determine optimal pillar spacing and track height. The economic impact of this project is massive. Before the railway, transportation across the Mongolian desert relied heavily on highways vulnerable to sand blockage and seasonal disruptions. Travel times for freight could stretch unpredictably, affecting supply chains. The elevated railway now offers a stable, high-speed corridor that connects inland regions to major industrial hubs and ports. This improves trade efficiency, reduces fuel consumption compared to truck transport, and strengthens regional economic integration. Beyond economics, the railway carries strategic significance. Infrastructure of this scale enhances regional connectivity and reinforces long-term development goals. Remote desert regions once considered isolated now have access to faster transportation, opening opportunities for tourism, mining, renewable energy projects, and cross-border trade. The visual impact of the railway is extraordinary. Stretching across endless sand dunes, the elevated structure appears like a silver line slicing through golden terrain. From aerial views, it resembles a giant ribbon cutting the desert into two halves. At sunset, the pillars cast long shadows across the sand, symbolizing the intersection of nature and modern engineering. Construction was completed in phases, with different sections opening gradually. Each completed segment represented a milestone in overcoming desert engineering challenges. Engineers gathered valuable data from early sections to improve later phases, refining foundation depth, wind barrier design, and maintenance strategies. Maintenance remains a key focus. Although the railway is elevated, desert conditions still demand constant monitoring. Robotic inspection vehicles travel along the tracks to detect micro cracks or structural wear. Sensors measure vibration, temperature, and wind stress continuously. This predictive maintenance approach reduces downtime and extends the lifespan of the infrastructure. Energy efficiency also plays a central role. The railway operates using electrified tracks powered partly by renewable energy sources, including solar farms built near the desert corridor. The abundant sunlight in the region provides an ideal opportunity to integrate clean energy into railway operations, reducing carbon emissions compared to traditional diesel transport. Critics initially doubted the feasibility of such an ambitious project. Many questioned whether it was economically viable or technically sustainable in such extreme conditions. But today, the 2,700-kilometer elevated railway stands as proof that modern engineering can overcome even the most hostile environments when backed by research, innovation, and long-term planning. The project also serves as a model for future desert infrastructure worldwide. As climate change increases desertification in many parts of the world, similar elevated transport systems may become more common. Lessons learned from this railway, about foundation design, wind resistance, and environmental protection, could influence infrastructure development across Africa, the Middle East, and Central Asia. In the end, this was more than just building a railway. It was about transforming geography itself. By lifting steel and concrete above the shifting sands, engineers effectively carved a permanent path through a landscape that once resisted human settlement. The Mongolian Desert, once a symbol of isolation and harsh survival, is now crossed by one of the longest elevated railways on Earth. And perhaps the most remarkable part is not just its length, 2,700 kilometers, but what it represents, a bold vision where technology meets ambition, where deserts are no longer obstacles but frontiers of innovation.